Welcome to my channel. So today we are going to discuss about the FIR filter design using the windowing technique. Okay, so in the previous video, the steps to be followed in order to design the FIR filter using the windowing technique we discussed. Okay, so if you want to learn that video means I will give a given link in the description box. You can refer it. Okay. So now the first problem. So it's a May 2017 and November 2010 question. So this question is similar to the Fourier series method except only the two steps. Okay, except the second step and third step is different in this method. Okay, so already we solved this same problem in Fourier series method. Now we are going to solve this problem in Hamming window. So you see the question, design a high pass filter with the following frequency response HD of e power j omega equal to 1 for the modulus of omega between pi by 4 to pi, 0 otherwise, okay, of length capital N equal to 11 using Hamming window. Okay, so if this windowing method is not mentioned means um, we can use the Fourier series method, but here using Hamming window they will mention. So we have to use this particular window. Okay. So what are these steps to be followed in the design of FIR filter in windowing technique? So the first step is to using this HD of e power j omega, we have to find the small HD of n. Okay, the desired impulse response we have to find out. Okay, so first we can draw the graph for this HD of e power j omega. So you see, so what is HD of e power j omega? It is 1 for the frequency modulus of omega. Okay, so here you just see this is modulus of omega between pi by 4 to pi. Okay, that means modulus of omega means it takes the negative value as well as the positive value. So that's why we can write this thing into two things. One is the minus pi to minus pi by 4, that HD of e power j omega is 1. Okay, similarly pi by 4 to pi, this HD of e power j omega is 1. Then in between the minus pi by 4 to plus pi by 4, this value is 0. Okay, so this is the frequency response is given. Okay, so from using this, first we have to, the first step is to we have to find the desired impulse response HD of n. Okay, so what is the formula? So you're familiar with this formula. Already we solved the 4 problems in Fourier series method. Okay, so the HD of n is equal to 1 by 2 pi integration over the limit minus pi to pi HD of e power j omega into e power j omega n d omega. Okay, so here we have to substitute the value of HD of e power j omega over the limit. Okay, so here you see, so you see the graph, the HD of e power j omega is 0 for the limit minus pi by 4 to pi by 4. Okay, so for this limit, for minus pi to pi by 4, the amplitude is 1. And pi by 4 to pi, the amplitude is 1. So that's why we can split this integration minus pi to pi into 3 limits. In that, in 2 limit, the HD of e power j omega is having the value 1. In this interval, the HD of e power j omega is having the value 0. Okay, so that's why we can split this integration as minus pi to minus pi by 4. What is the HD of e power j omega? 1. Okay, into e power j omega n d omega. Okay, plus next from pi by 4 to pi. Okay, the lower limit pi by 4, the upper limit pi. So pi by 4 to pi, the HD of e power j omega is 1 into e power j omega n d omega. Okay, so next you just integrate this one. So if you are integrating e power j omega n, we can get e power j omega n by jn. Okay, with the limit minus pi to minus pi by 4. Plus, if you are integrating this, similarly say the same answer with the limit pi by 4 to pi. Okay, then you substitute the upper limit and the lower limit, upper limit and lower limit, we can get like that. Okay, and this jn, you take it outside. So we can write 1 by 2 pi jn e power minus jn pi by 4 and this. Okay, and we have to combine this two term and this two term. We have to combine. So you just see, if you are combining first this two term, e power jn pi minus of e power minus jn by and this 2j. Okay, you give it to here. So divided by 2j. And if you are combining this first and last term, so taking minus as common, e power j n pi by 4 minus e power minus j n pi by 4 divided by 2j. Okay, so you see, already you know what is this? This is in the structure of sine theta. E power j theta minus e power minus j theta divided by 2j. It is called as a sine theta. So in the place of theta, which one is available? N pi. So we can write, instead of this term, we can write it as sine n pi. Okay. Similarly, instead of this, we can write it as sine n pi by 4. Okay. So center one minus is available. So HD of n is equal to 1 by pi n sine n pi minus sine n pi by 4. Okay, so this is our desired impulse response, and this impulse response is having the value for n is between minus infinity to infinity. Okay, so the first step is over, and here we are going to design the FIR filter, finite impulse response, for the capital N is equal to 11 sample. Okay, so that's why we are going to find the answer for this HD of n for the first center 11 value. So center 11 value means that is the n varies from minus of n minus 1 by 2 to plus n minus 1 by 2. Okay, that is the meaning. So what is n minus 1 by 2? So 11 minus 1 by 2. So 11 minus 1 by 2 means it is 5. Okay, so for the n between minus 5 to 5, we have to find out this HD of n value. Okay, so you see, so here the filter coefficient, that HD of value we are going to calculate. So first for n equal to 0. Okay, so for n equal to 0, that is in this formula, we have to put n 0. So if you are substituting directly n 0, we can get 0 divided by 0. It is indeterminate answer. Okay, so already you know, for n equal to 0 only, we have to follow the different procedure. For remaining, we can follow as usual. Okay, so if directly substituting, we can get the indeterminate answer. So that's why, so you know, the HD of 0 equal to limit n tends to 0, the first term, minus limit n tends to 0, the second term. So already you know the structure, limit n tends to 0, sine theta divided by theta, the answer is 1. Okay, similarly here, pi by 4 is available, so you just multiply 1 by 4 to the numerator and denominator. Okay, so except this, so sine of theta divided by theta equal to 1. Okay, so what is the answer for the second term? 1 by 4. Okay, so 1 minus 1 by 4, so the answer is 0.75. So the HD of 0 is 0.75. Okay, so already we discussed the same problem in the Fourier series method in a detailed manner. Okay, similarly we have to find, for n equal to 1, we have to find out. So, you know, according to the HD of e power j omega graph, the corresponding impulse response is also symmetric about the 0 axis. Okay, so that's why the HD of 1 and HD of minus 1, if you are calculating, we can get the same answer. So only one time you just calculate. So HD of 1, what is HD of 1? In this HD of n formula, you just substitute, instead of this n, you just substitute 1. Okay, so sine pi minus sine pi by 4 divided by pi into 1. Okay, so instead of n, we have to put 1. So what is the answer for this? You just use the calc in radian mode. First, you put your calc in radian mode and you just type this one. We can get the answer is minus 0.225. Okay. Similarly, for n equal to 2, that is HD of 2 and HD of minus 2, both are equal. So if you are substituting, instead of n, we can substituting 2 means we can get the answer is minus 0.159. Similarly, for n equal to 3, we can get minus 0.075. For n equal to 4, we can get 0. For n equal to 5, we can get 0.045. Okay, so the 11 HD value we calculated. Okay, HD of 0, it is unit. 1 minus 1 equal, 2 minus 2 equal, 3 minus 2 minus 3 equal, 4 minus 4, 5 minus 5 we calculated. Okay, so the first step over. And the second step, what is the second step? We have to use the window. So which window in problem given? Hamming window is given. So the Hamming window sequence we can define. So the Hamming window is nothing but the WH of n is equal to 0.54 plus 0.46 cos 2 pi n by n minus 1 for the modulus of n between n minus 1 by 2. Okay, so here the capital N is given as 11. So for the small n between minus 5 to pi, this WH of n we have to find out. Okay, for each n value we have to find the windowing discrete value. Okay, so you just substitute. So first to put n equal to 0. So if you are substituting n equal to 0, 0.54 plus 0.46 into cos 0. Okay, so what is the value of cos 0? 1. So 0.54 plus 0.61. Okay, so already I told you know in any windowing sequence at n equal to 0, that corresponding window is having the maximum value 1. Okay, whenever the n value increases or decreases in negative side, we can get the amplitude is decreases. Okay, so you see this is 1, n equal to 1, 0.912, n equal to 2, 0.68, so decreases. So next we have to calculate WH of 1, okay, at n equal to 1. So 0.54 plus 0.46 into cos, instead of n, you just put 1, so cos pi by 5. So the answer is 0.912. Similarly, WH of 2 equal to 0.682. Then WH of 3 equal to 0.398. WH of 4 equal to 0.1678. WH of 5 is equal to 0.08. Okay, so you just check the answer. So the center answer, okay, at n equal to 0 answer is maximum. Whenever the n value increases, this windowing sequence value decreases. Okay, you see 1, 0.9, 0.6, 0.3, 0.1, 0.08. Okay, so in this thing only we can get. And similarly, you know, according to the property of window, this WH of 1 and WH of minus 1 both are equal. Similarly, WH of 2 and minus 2 equal, 3 minus 3 equal, 4 minus 4 equal, 5 minus 5 equal. So the second step over. Okay, and what is the third step? So in order to obtain the finite impulse response, we have to multiply the desired impulse response with the windowing sequence. Okay, so the H of n is equal to HD of n multiplied with W of n for the same n value. Okay, so for a small n is between minus 5 to 5, we have to multiply. Okay, so you see, so the H of 0. Okay, so already we derived the H of n value for minus 5 to 5. Okay, we are having, and the W of n value already we derived for minus 5 to 5. So you just multiply the each value. So you see, so H of 0 is obtained by multiplying HD of 0 with W of 0. What is the W of 0? 1. HD of 0, 0.75. So the answer is 0.75. Similarly, the H of 1. Okay, so H of 1 and H of minus 1. Both are equal. Okay, H of 1 or H of minus 1 is multiplied by HD of 1 with W of 1. So if you are multiplying, we can get the answer is minus 0.2052. Similarly, the H of 2 and H of minus 2. Both are equal since HD of 2 and W of 2 is equal. Okay, so if you are multiplying, we can get the answer is minus 0.1084. Okay, similarly, H of 3 and H of minus 3 is equal. So you just multiply the HD of 3 with the W of 3. So we can get the answer is minus 0.03. So H of 4 is 0 and H of 5 is minus 0.0036. Okay, so this is the answer. Okay, this is the desired our impulse response for the n value between minus 5 to 5. Okay, then after calculating H of n, what is the next step? We have to find the transfer function. Okay, so transfer function, you know the formula. The transfer function for the symmetric FIR filter is H of 0 plus summation n equal to 1 to n minus 1 by 2. Here n minus 1 by 2 is 5. H of n into z power minus n plus z power plus n. Okay, so then you substitute this H of 0 and H of n value here. So you just expand it. Okay, so here the H of 0 value is 0.75. Then plus, so you just expand it. Okay, then you substitute the value h of 1, h of 2, h of 3, 4 and 5 value. So you see, we are substituting. Okay, then you see this transfer function. This transfer function is having negative z power as well as the positive z power. Okay, that means this is not a physically realizable filter. Okay, so in order to convert the physically realizable filter, so we have to multiply the h of z with z power minus of n minus 1 by 2. Okay, so we have to multiply the transfer function with z power minus of n minus 1 by 2. So the h dash of z is equal to z power minus 5 into this h of z. Okay, so you just multiply each term. So 0.75 into z power minus 5. Then you multiply each term. Okay, so we can get like this. So you see here all z powers, we are having the negative value, not the positive value. Okay, then you just expand it. Okay, so after that you just arrange in our that is ascending order. Okay, so that is first we have to write the constant. So this constant term, this constant means it indicates z power 0 term. Then z power minus 1 term is there, you just see no. Okay, then z power minus 2 term you just write. Then z power minus 3 term, z power minus 4 term, z power minus 5, minus 6, 7, 8 and z power minus 10 term you just write. So this is the transfer function of our physically realizable system. Okay, so in that, so from that the filter coefficients of the causal filter is given by, so you just see this constant and z power minus 10 coefficient both are equal. Okay, that means the h of 0 and h of 10 is equal. So it is equal to 0.0036. Okay, then h1 and here h of 1, that is there is no z power minus 1 term is there, z power minus 9 is not available. So h of 1, h of 9 is 0. Then h of 2, h of 8, z power minus 2, z power minus 8 term. You just see minus 0.03. Similarly, h of 3, h of 7, it is minus 0.1084. Similarly, h of 4 minus 0.2052. H of 5 is 0.75. Okay, so these are all the filter coefficients. Okay, we calculated. Then after that, we have to find the frequency response. Okay, so in the problem, if only design the filter means up to this you just write. Okay, so up to this you just write. If in the question, okay, so here in the question they are not mentioning the magnitude response, but if the magnitude response, plot magnitude response they are asking means, so you just follow the steps. Okay, so the frequency response is given by, so you know the formula. So this our given filter is a symmetric filter with a capital N equal to 11, that is odd. Okay, so odd means this is type 1. So for the type 1 filter, the frequency response is given by h of e power j omega equal to, already you know, n equal to 0 to n minus 1 by 2 a of n cos omega n. And here this a of 0 and a of n is calculated using this formula. So a of 0 is h of n minus 1 by 2. Okay, so if I am substituting n value, h of 5. So what is the h of 5 value? 0.75. Similarly, a of n, for remaining n equal to 1 to 5, you just use this formula. A of n is equal to 2 into h of n minus 1 by 2 minus n. Okay, so in that, first you put n equal to 1. Okay, you just calculate a of 1. So a of 1 is equal to 2 into h of 5 minus 1. Okay, that is 2 into h of 4. So we can get minus 0.4104. Similarly, a of 2 is calculated as minus 0.2168, a of 3, a of 4 and a of 5. Okay, so after calculating this coefficient, you just expand the summation and substitute it. Okay, so therefore, the frequency response h of e power j omega bar equal to first a of 0, 0.75, then a of 1. So a of 1 is minus 0.4104 cos omega, then a of 2 minus 0.2168 cos 2 omega, then A of 3 0.06 cos 3 omega, then A of 4 0, then A of 5 0.0072 cos 5 omega. Okay, so this is the frequency response of our given filter using Hamming window. Okay, so if you want to draw the graph means, so already you know the procedure, you just make a table for the omega ranges from 0 to pi. Okay, so for the omega ranges from 0 to pi, you just calculate the value of h of e power j omega. Then you convert into dB. Okay, using the formula 20 log of that particular answer. Then you draw the graph. Means we can get the frequency response. Okay, but in this question, so the frequency response they are not at all asking, only the design. So up to this it is enough. Okay, so this is the problem design of the high pass filter using the Hamming window. Okay, similarly, we can solve the same problem using Hamming window, rectangular window, and so on. Okay, the same procedure only the thing is the second step. Okay, the window we have to choose. Instead of this Hamming window formula, you just use Hamming window. Then you multiply each sequence. Then as usual procedure, you just follow. Okay, so this is about this is the very important problem. Okay, so similar to this problem, we will solve the next problem with a different specification in the next video. Okay, so thanks for watching my channel, and please subscribe my channel for more videos. If you want to learn all lecture videos related with this subject in my channel in the name of DTSP, discrete time signal processing or digital signal processing, the playlist is there. In that playlist all videos are available in order from unit 1 to this. Okay, so I will give link for that playlist in the description box. You can refer it. Okay, so thank you. We will meet in the next video with one more problem.